Hi guys, in this video lesson we're going to be talking about function transformations, which is actually a continuation of the transformation rules we learned last week with absolute value functions. So we're going to briefly talk about each of the parent functions before we actually get into transforming. So there are far more parent functions than we're going to discuss in this class, but once you get a feel for these parent functions, you should be able to extend your knowledge in further classes to further parent functions. So a parent function is simply the starting point. It's the most basic function for each type of function. So for instance, with the absolute value function, y equals the absolute value of x is the most basic absolute value function we can come up with. And we could plug anything we want into this function, although I know in Algebra 1 you mostly do -3 to 3. And when you do that, and you get these outputs, you can make coordinates from them. You say 0, 0, 1, 1, 2, 2, 3, 3. And that's the parent function for absolute value. Just like we did last week, nothing new there. The parent function for a quadratic, we actually studied a great deal last semester. Y equals x squared. And if you were to plug in those same domain values, those same input values for x, you would get 9, 4, 1, 0, 1, 4, 9. And so when you graph the parent function for a quadratic, you get -3 goes up to, I'm just going to 1, 2, 3, 4, 5, count up so I have a gauge. So -3 would go up to 9, -2 goes up to 4, -1 to 1, 0 to 0, 1 to 1, 2 to 4, and 3 to 9. And you get almost this elongated U shape. So just like last semester, once you have this nice symmetric U shape with a vertex and an axis of symmetry, you know that that's a quadratic. Sometimes quadratic functions are called square functions because x is being squared. The next parent function is a cubic function. So y equals x cubed. So if we use those same domain or input values, we would get a range of -3 cubed is -27, -8, -1, 0, 1, 8, and 27. And we know that graphing 27 would be quite difficult on the space I've left myself, but that's okay because we know by putting arrows at the end of a function that it tells us that it continues on infinitely in either direction that we place an arrow. So 0, 0, -1, -1, -2, -8, and -3, -27 goes off the graph, which is definitely not a problem because we can just put arrows at the end of our function to show that the domain and range continue. The next parent function is of a square root, so y equals the square root of x. And the interesting thing about a square root, like we learned way back the first marking period of school, is if we take the square root of a negative, we'd get an imaginary number, which could not be graphed on the typical coordinate plane. A Cartesian plane just graphs real numbers, unless we add an imaginary plane, which is a whole different topic for a different day. So I picked these strategic values because I know the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, and the square root of 25 is 5. And because I picked those particular values, I knew I would come out with clean, integer, real numbers that could be easily graphed. So I'm just going to make tick marks at every interval of 5 for more simple graphing. You don't have to do this. It's just a strategy that I tend to use. And then I know 0 has an output of 0, 1 has an output of 1, 4 has an output of 2, 9 has an output of 3, way over here it's 16 has an output of 4. Oftentimes with square root functions, and same thing with a cubic function or a quadratic, you may not graph a ton of points. I would expect to see enough points that your curve follows the same general shape as the original parent does. Like this graph should not be a straight line, it should have a curve to it. Interesting enough, this domain is 0 is less than or equal to x is less than infinity, and the range is 0 is less than or equal to y is less than infinity. A little different than the domains and ranges we did with absolute value functions. So the cubed root function, I can take the cubed root of a negative. In fact, I can take the cubed root of any odd, or sorry, I should say, you can take the root of any odd value. So a cubed root, a fifth root, a seventh root. So my domain in this function ends up becoming my range from my cubic function. They're just flip-flopping. They're inverses of one another. So again, I'm just going to give myself a few tick marks as guides, reference points. Okay. So I can say that the cubed root of negative 27 is negative 3. Does not fit well in my graph. But the cubed root of negative 8 is negative 2. Negative 1 is negative 1. 0 is 0. 1 is 1. 8 is 2. And it follows this general shape where there's kind of a concave up situation on the left of the origin and a concave down situation at the right of the origin. So my curve isn't perfect, but I can tell there's a curve to it. So let's get into some examples here. So how about for example 1, we start with a quadratic. We do y equals 2x minus 10 squared. I know a lot of you had lots of questions about stretching and shrinking last week. So if we think of our HSRV here, our transformation list, the order of operations for transformations, we're going to go right 10, and we're going to divide our x values by 2. And those are our only transformations. So I'm going to start by making a parent function. So my parent has this curved parabola shape to it. And then I'm going to shift the whole thing right 10. And then I'm going to divide the x values by 2. And I should have made that a different color. I'll pretend I made it red. And so when I divide 10 by 2, I get 5. When I divide 9 by 2, I get 4.5. And then when I divide 8 by 2, I get 4. So I get this really tall, skinny parabola. Next, let's do a cubic. Let's do 2x cubed minus 5. So I have no horizontal shift. I'm multiplying the y values by 2. No reflection. And then down 5. So I'm going to start with my cubic parent. 2 goes to 8, and negative 2 goes to negative 8. So it's already kind of tall and skinny to begin with. And then I'm going to double my y values. So 0 stays at 0, but 1 goes to 2, and 8 would go all the way up to 16. Hard to get on that graph, right? But I know it's getting taller and skinnier. Stretch pulling in height. And then I'm going to shift the whole thing down 5. So I've got this tall, skinny graph shifted down 5. So I'm going to look and see if I haven't done any reflections yet. This next two, I'll do some reflections. Let's do y equals the square root of negative x. Let's do plus 8. So my horizontal shift is left 8. Oop, there's no stretch. My reflection is over the y-axis because the negative is inside the grouping symbol, and then there's no vertical shift. So I'm going to start by making my parent function. And then I'm going to reflect over, oops, sorry, I'm going to shift left first. I'm going to skip that step. So I'm going to move left 8, 2, 3, 4, up 2, 5, 6, 7, 8, 9, up 3. Shift to the left 8, and then I'm going to reflect over the y-axis. 2, 3, 4, 5, 6, 7, 8, 9. Oh, put my vertex at the wrong point there. Go back a step. Okay. So this goes over here. This starting point of my square root, not really my vertex, but my starting point for my square root, is at negative 8, 0, so it would reflect over here to 8, 0. 2, 4, 5, 6, 7, 8, 9. Okay, one more. So this last one, let's see, I'm going to do y equals, let's do negative x plus, actually we need a cubic, we haven't done one of those. Negative cubed root of x, let's go down 6. So let's go through my parent function, my transformations. Horizontally, I have no shift, no stretch. I'm going to reflect over the x-axis, and then down 6. So I'll start by making my parent. Okay, so my parent looks something like this. And then I'm going to go over the x-axis, so these flip-flop, which is actually kind of an interesting function because whether you reflect over the x or the y, you're going to end up with the same shape. And then I'm going to move down 6. And if you notice today, I gave all of your function examples 2 steps. And that is the same for the assignment we're starting today. Just gives you a good gauge to see if you're following, if you caught all your transformations.